Hello everyone, let me introduce myself. I am Nitin P, a 4th semester student from Chemical Engineering Department. I will be explaining the topic instrumentation of UV visible spectroscopy in today's video. These are the contents we will be discussing today in today's video. Yes. Let me start with the introduction part. Basically, UV spectroscopy is used to measure the absorbance in UV region, that is it's a range of about 200 to 400 nanometer, and visible region 400 to 800 nanometer. The overall range is about 200 to 800 nanometer. In which in this spectrum basically there is a electron transitions in atoms and molecules. It works based on the absorption of UV and visible light in chemical compounds. In this the molecules containing bonding and non-bonding electrons can absorb energy in the form of ultraviolet or visible light to excite these electrons to higher anti-bonding orbitals. It's basically used in the identifying the concentration of in absorber of analytes or the solution using the Beer-Lambert's law. It's also used in chemistry for quantitative determination. This is the picture of UV visible spectroscopy, and this is the following instrumentation part we'll be looking after. We'll follow up with the instrumentation part. This following picture represents the instrumentation of UV spectroscopy. UV spectroscopy runs on major four parts. It is split into four parts basically. First, this part is actually um, yeah, this part is actually the light source, where the light is emitted from deuterium lamp, tungsten lamp, also hydrogen lamp. The next part is for the wavelength selector. Where the filters and monochromators and further things are used. And the third part is the sample holder, where the sample liquid is placed. The fourth part is detectors. It's used to detect the presence. These are the major that four parts. Let me start one with the first part, that is the light source. Yeah. Before discussing, let's tell what these features are. This is the hydrogen lamp. This one is the deuterium lamp. This is a tungsten halogen lamp. First of all, we'll start with the radiation sources. Here, the gas molecules get excited by electron collisions to emit line, band, or continuous spectra, depending on the internal pressure. Where the pressure is low, line spectra are emitted, but hydrogen, deuterium, xenon discharges lamps and make mercury vapors. Further is UV light sources. Here it is a high pressure hydrogen and deuterium lamps which emits UV radiations via electron discharge. With deuterium offering much higher intensity at a higher cost, it should be stable and provide sufficient intensity. Comparatively, deuterium performs well than the hydrogen lamp. Also, it is costlier than hydrogen lamp. Right. Next, it's a visible light source, the tungsten halogen lamp. It's in a range of 250 to 2500 nanometer. In this lamp, the tungsten filament evaporates. This one, tungsten filament evaporates. Evaporated tungsten combines with halogen gas to create tungsten halogen molecules. Basically, it is formed by that it is formed, right, and through chemical cycles. The tungsten halogen molecule migrates back to the filament. Tungsten is redeposited and recycled into the filament, onto the filament, onto this filament. So second one is wavelength selector after the light source. First of all, as per the UV spectroscopy instrumentation picture, first comes is the filter. Filter selects a specific wavelength band by allowing a certain colors of wavelengths to pass through the colored glass or dye. Yeah, in the absorption filters are made up of colored glasses and dye basically. Further is the monochromatous, which helps in converting the polychromatic multicolored lights into monochromatic, that's a single color light. Simply to say, it's like prisms, the reverse of prisms. Except you can imagine about it. The next part is the slits. Slits, we have both the entrance slit and exit slit. The slits are narrow openings between metal jaws that control the passage of radiation. The collimators. Further, these collimators, it focuses light from the entrance. Whatever the light is passing through, it focuses into a parallel rays. Look, these are the parallel rays focused by the collimators directed towards a dispersing medium. Yeah, dispersing medium is the dispersing elements such as previously as I said is prisms or diffraction grating, which isolates radiations of desired wavelength from the wavelength of continuous spectrum. Yeah, diffraction grating reflects the wavelengths at various angles based on the orientation of the grating. Yeah, as we see here, there are various wavelengths being diffracted. Further, the focusing mirror direct a narrow band of isolated wavelength toward the exit. Basically, whatever the light diffracted from the diffraction grating are focused, yeah, with the help of focusing mirror, it is directed towards the exit slits. Yeah, next, by this, the wavelength selection is achieved. Just alignment of this direct diffraction grating. Third is a sample holder. Where sample holder is basically where we keep the liquid sample which we created during the experiment in the instrument. That holder is called as cuvettes. Yeah, this is cuvettes. Yeah, the pictures are like this. This is the picture of cuvettes. Cuvettes is basically its function is used to handle the liquid samples during spectroscopy. And the shape, as you see, it's a rectangular. Sometimes it might also be cylindrical in design. Optical, if you see, it's a transparent with minimal light absorption features. It can be made up of two materials. Basically, one it can be glass or quartz based on the suitability. Further, it can hold up to 1.5 ml to 3.5 ml volume of sample. Um, but for every trial, we should clean it. It can be cleaned by using distilled water, dilute alcohol, or acetone. Yeah. If you see here, yeah, based on design features often feature two transparent faces. This is a transparent face and this is an opaque face. Yeah. The fourth part is detectors. This is one of the kind of detectors. Detector means it's a transducer that converts UV visible radiant energy into electronic signals with high intensity. Here, the photon transducers are used for UV visible region. An ideal transducer should have high sensitivity, high signal um, to noise ratio, and a constant response to radiation over a wide range of wavelengths. There are, yeah, they are of three types. Yeah, first one is the barrier layer cell, which generates a voltage when light strikes the semiconductor interface. This is the picture of barrier layer cell. The barrier layer cell consists of a semiconductor such as selenium, which is deposited on a strong metal base, such as iron. Look, if you can see, the iron is marked here, and it also contains a thin layer of aluminum or silver, basically silver. And the accumulation of electrons on the silver surface produces an electrical voltage difference between the silver surface and the base metal. If the external circuit has a low resistance, a photocurrent will flow which is directly proportional to the intensity of incident radiation beam. The next is photoemission tube. Uses incident light to eject electrons from a cathode. Yeah. Next is photomultiplier tube. Amplifies ejected electrons using multiple diodes for high sensitivity. Diodes. Diodes have the property of emitting more than one electron when struck by a single electron. They serve as an electron multiplier through secondary emission. In If you look into the photomultiplier tube, they have the high intensity as we discussed previously. It is useful for measuring even radiations for low frequency. It contains three parts, that is evacuated glass tube, cathode, anode. Further, additionally, electrodes known as diodes. That is the one which I explained previously. That's all. Okay. Thank you.